Good evening, ladies and gentlemen. Here's our little slideshow here for you. This is a slide called Hacking the iPhone. A little bit of history here about our little crew. We're formed in June 2007, just before the release of the original iPhone. We're original hardware hackers and device enthusiasts based around Apple products, and we sort of gravitated towards the iPhone as a platform. We exist on IRC, and this is the first time most of us have met each other. Originally, there was a couple of channels on the osx86.hu server. We've got a wide membership: Germany, Belgium, France, Russia, Hungary, USA, Israel. And during those initial few months of the iPhone first generation, DHL and FedEx shipped around a lot of US phones to us. So we've got some statistics here of our little site. We've had about 1.7 million visits in the last month, 60,000 unique visitors per day, and various networks around. We've got a tool called Pwnage Tool and another tool called QuickPwn, which is viewed here as an Xcode project. It's a Cocoa application. It's got 20,000 lines of code. QuickPwn has got 15,000 lines of code. There's also other platforms, Windows and Linux as well. We've had 3.6 million Sparkle updates since we last deleted our logs, which was in the 16th of July. We try to release patches when Apple release an iPhone update. We try to get patches out 24 to 48 hours after the release of those updates. And the modular bundle set for cross-platform use. We use Sparkle for updates for the Mac platform, as I mentioned. Oh, sorry. And interestingly, there's 180 very active users from Apple who update their QuickPwn and Pwnage tool on a regular basis. So I think they like our software, which is pretty cool. So thank you very much, Apple. So I'll hand over to... Oops, sorry.
Not that far yet.
Yeah, sorry. I'll hand over to... Well, I'll just introduce my colleagues here. We've got Bushing on the end. He's one of the guys. This is MuscleNerd. And this is planetbeing. I don't know why, but this is planetbeing. And we've got a bunch of other guys here who don't want to be identified for obvious reasons. But hello.
Right there at the end.
Yeah, they're over there. Yeah, wearing Pwn Apple T-shirts, and they speak Russian. So say hi, guys. So. So without further ado, I'll hand you over to planetbeing, who's going to talk a bit about the applications processor side of the iPhone. Thanks.
So my talk is going to be about the applications processor side, and that's the chip that runs the iPhone OS and all the racing car games that you see in the App Store. It's unrelated to the baseband unlock because the iPhone has two ARM processors, and the baseband modem has one of them, and the applications processor has the other one, and they're only loosely connected, and they each have their own security framework. So my portion of the talk, I'll be focusing on the application processor. And our goal is to execute custom code on the iPhone OS. The purpose of doing so is to launch third-party apps, activation of the iPhone, which allows the iPhone OS to recognize unsupported, unofficial carriers. And it also provides a useful platform for the SIM unlock, because then we can use the iPhone OS to directly communicate with the baseband modem. So I'm going to just go over some of the security framework of the iPhone. And first of all, I'm going to talk about the basic software architecture of the device. As Apple advertised, the iPhone OS architecture is basically Mac OS X. If you look at the disassembly of the kernel, you can see that it's basically XNew, which is the kernel for Mac OS. It's basically XNew code compiled for ARM. A lot of the userland architecture is also the same. There's launchd, which is the Mac OS version of init, like Linux's init. It's a little lobotomized. There's no command line switches, but it's basically the same thing. You have launch daemons and everything else. System libraries are slightly modified, but they're pretty much the same as on a typical OS X Mac machine. Instead of the Finder, you have Springboard as a shell. One important difference between the Mac OS X version of the Mac version of OS X and the iPhone OS is that there's an additional daemon called lockdown-d, and it handles communications with the computer. It basically is the gateway between the computer and the iPhone over the USB cable. It multiplexes the USB connections, and it establishes an SSL tunnel between a socket on the computer and on the iPhone. And it's basically like inetd. You can have different services that lockdown-d activates, services like mobile sync, mobile backup, and a rather important one for our purposes called AFC, which allows the computer to access a small jailed portion of the file system. So our goal here is to sort of subvert this and to modify the operating system so that we can run our own code. How do we do this? The iPhone OS runs on a NAND, primarily runs on a NAND flash disk. To userland, it appears as a normal block device. So if you're familiar with the Mac OS terminology, it's under /dev/rdisk0s1/dev/rdisk0s2. There's two logical partitions on the NAND drive. There's a system partition, which is mounted at root, and there's a user partition. The system partition is read-only, and these are only logical partitions, and they sit on top of an FTL, which convert the logical partitions, which are better suited for traditional disk drives, to NAND flash geometries, which have peculiar things like being only able to erase a block at a time. So here's how the iPhone OS is protected. Third-party applications and everything else that's modifiable on the iPhone OS are installed on the user partition. The system partition is read-only, so in case the iPhone crashes, you don't have to recheck the system partition for file system integrity. Every program, every executable on the iPhone is signature checked by when the system call execv is executed on it. All executables must be signed by Apple, and the signatures and hashes are stored in the Mako format as segments. And because the signatures are only checked when the program starts, you can still use code execution exploits if you have a buffer overflow or a stack overflow. But the limitations of that is that all the applications, like mobile Safari or mobile mail and everything else, run as a mobile user, so they can't really alter the operating system. The code signing, these signature checks are implemented inside the kernel. So in order to do our thing, in order to run third-party applications, we have to modify the kernel. Here's how the kernel is protected. The kernel is stored on the system partition, which is mounted read-only. It's a big binary blob with the kernel and all the kernel extensions, kex, which are basically provide the driver functionality for Mac OS X. And they're all concatenated together and compressed with LZSS and encrypted and signed. And you can't alter this kernel cache except as root. So even if you had a code execution exploit, you still need a privilege escalation exploit as well in order to modify this file. And even if you could do that, the kernel cache is signed. So if you modify it, your system will stop booting. So to get around that, we need to sort of look at how the signature for the kernel is checked. And I'm just going to briefly take you through the boot process for the iPhone. The first piece of code that's loaded on the iPhone is the boot ROM. It's secure boot, as Apple's terminology is. And Name is kind of a lie, as you'll find out later. So the first thing that it does is it loads from NOR flash a program called LLB. The NOR flash supplements the NAND flash. So just an 8 megabit NOR flash, and it serves as the NVRAM for the OS, which includes kernel panic logs, bootloader variables. It also has a file system, well, kind of a rudimentary one, a list of images that contain the bootloaders themselves. So the LLB is, like, the way I put it is that it's the MBR for the NOR, which it does the same thing that the MBR does on like an x86 machine. It reads the image list format, and it loads the next stage bootloader from the image list, signature checking it first before executing it. The next stage in the boot process after LLB is iBoot, which is loaded from the image list. If you're familiar at all with the Mac boot process, iBoot is analogous to open firmware. On a Mac machine, instead of the kernel probing devices and discovering what hardware is there, the bootloader provides the kernel with a device tree, which has all this information already included. And iBoot loads a device tree from the NOR. The device tree there's one for each different type of platform. One for the iPhone, one for the iPhone 3G, and one for the iPod Touch. And this device tree is only partially populated. There's still some platform device-specific things, like the serial number that must be added by iBoot. Also, Apple uses different components from different vendors during the manufacturing process. There will be like a few different types of LCD panels that they use and a few different types of NAND chips from different vendors. And some of them have their own initialization sequences. Instead of having the kernel do that, iBoot actually does that, which makes the kernel more flexible. So it populates the device tree with gamma tables, Wi-Fi calibration data. It does all of that. And then finally, it loads the kernel from NAND and executes it. The thing here is that iBoot checks signatures on everything. It checks signatures on the kernel, it checks signatures on the device tree, and even the boot logo and graphics that it displays. So we need to get around this in order to do our eventual goal of running unsigned applications on the iPhone. And the whole structure works like this. You have this whole chain that signature checks the kernel, and then the kernel signature checks all the userland applications. So there's one slight problem with this scheme. We know that userland applications are signature checked by the kernel. That's just good. And the kernel is signature checked by iBoot, so that's good. iBoot is signature checked by the LLB. Okay, but is the LLB signature checked by the boot ROM? No. So that's a big problem. So all we need to do is just flash our own LLB and then patch out the signature checking on all the subsequent stages, and then we can run our own code. This is a little bit easier said than done, though. So, okay, so the next part is the only way we can flash the NOR is through the restore process, and I'll explain why in a second after I tell you what it is. Every stage in the boot process that I described earlier can abort to either a DFU or recovery mode, and it's activated by either key presses or if the next stage can't load. Recovery mode is basically a USB or serial console. It's a feature of iBoot, and DFU mode is just the mode where iBoot can be loaded and you can get into recovery mode. So the restore process is basically a version of iBoot is loaded, a newer version of the latest one is loaded by iTunes onto an existing version of iBoot or DFU mode. And then iTunes sends the latest kernel and a restore RAM disk to this iBoot. And then iBoot boots the kernel from the RAM disk. The restore process itself is actually conducted by this RAM disk kernel combination, a lockdown D daemon called restore D, the lockdown D thing as I described. It communicates with iTunes. It downloads an ASR image. I don't know if you guys know about ASR, but it's an Apple backup thing. ASR image from iTunes, and also downloads NOR firmware to be flashed. And the good thing about this process is actually very well designed. It's pretty much impossible to brick the iPhone because of this process, because you can, at any point, brick the applications processor, that is, at any point, because you can always bootstrap the restore process like this. Okay, so the way that this restore process is protected is that iboot that's loaded from any stage is signature checked before being executed. The RAM disk and kernel are also signature checked by iboot. And restore D itself signature checks the ASR image and the NOR firmware. And restore D sits on a signature checked RAM disk, so it itself cannot be normally modified. Also, everything is encrypted with something with a key that's derived from a hardware AES key. This AES key, we can't read it, but the code on the iPhone can use it. These keys are disabled from a non-secure boot, from any boot that's not from a signed RAM disk. So this means that even if we were able to find a code execution exploit in userland on a normal boot and have a privilege escalation exploit and communicate with the kernel and try to tell it to flash the NOR, we still can't do it because we're not in a secure mode. The file system itself is encrypted with file vault, and the way that's done is the file vault key and also the expected SHA hash of the file system is stored on an encrypted RAM disk. And this way, everything is encrypted, and it makes it difficult for us to do our work because we can't read any of the code and we can't reverse engineer it. So that's the way that they planned it. So it still sounds pretty secure. All the modification this graph shows all the modification vectors for every piece of the software that I mentioned. And you see that everything signature checks everything else pretty much. So it's still pretty secure even if the boot ROM doesn't signature check LLV, as long as you can't modify a NOR. Well, there's one problem, and is that this chain can be broken, and what better place to break it is than at the boot ROM level, where they can't patch it or fix it in any way. So it's pretty much your standard stack exploit, stack overflow exploit. They store, as they're processing the certificates, which are in a DER format, they copy all the certificate information onto the stack, but the signature itself is copied into this data structure without any sort of bounds checking. So then you have this classic stack buffer overflow, and then you just make the signature checking function return true. So I'm just going to show you, I probably don't have enough time to do a very thorough job of this, but basically this is the function that we want to return true. We want to jump to offset 57EC and make R4 1, because R4 gets moved into the return value later. Check certificate and get secure boot ones is the function that has the vulnerability. As you can see, in the highlighted areas, it makes space on a stack for 3 certificate structs. So these certificate structs, so what you want to do is construct a certificate DER that that's structured like this. There's the padding to fill out the thing that's overflowable is cert signature value. So you have 0x30 bytes of padding at the end to cover the rest of these, and then you can start loading the registers with your own exploit values. So 1 for R4, we don't really care about the other registers, and the offset 57EC for the PC, for the program counter. So that's basically our exploit. So what we use to do, what we load from this is what we call pwnage, which is our complete solution, as it were. What we do is we patch every single stage, like where I mentioned all the signature checks, we patch all of those out. And what we do, we patch it out in the LB, iboot, kernel, the restore D on the RAM disk, and on the file system image, because we patched out the signature checking on restore D, we can put our own sort of app store for unsigned programs, for things that Apple won't support. And the 2 most popular ones are Cydia and Installer. So we use we use the DFU exploit to load a version of iboot that doesn't perform signature checking, and then we use a normal restore process to to restore the rest of it, to flash the rest of this onto the iPhone. And what ends up happening is that we can use iTunes to flash our own custom firmware onto the iPhone. So, yeah. So just briefly, I'm going to just mention stuff that Apple did wrong to make the job easier for us. And probably the biggest reason is that instead of rolling out all this wonderful security mechanisms at once, they did it piece by piece, and they sort of made a few mistakes early on in the process. And that way, by doing so, they allow us to get access to pieces of code, and we were able to reverse engineer it, and we were able to figure out how it all worked and where the vulnerable points are and how to attack it. One of the early mistakes is in 1.0.2, the iPhone actually trusted iTunes, which we can modify easily. And at that point, we could actually send custom restore commands and jailbreak the iPhone. None of the executables were signed at that point, so you can make a simple file system alteration in your jailbroken. Another vulnerability in 1.1.1 and 1.1.2 is that everything used to run as root. So if you find a vulnerability within any sort of userland program, then you have root. And then they also left some interesting things like dev kmem, which means that we can poke and peek kernel memory and execute kernel code. So that's kind of bad. And finally, probably the mistake that first allowed pwnage was they left the boot arguments PMD and VMD. And these boot arguments can construct a RAM disk to boot from out of anything. And that basically allowed, not out of anything, but out of any contiguous portion of memory. And that allowed us to bootstrap a RAM disk pretty easily. Because when we upload a RAM disk, it has to be, the iPhone has to store it in memory somewhere, and then signature check it, and then decide whether it wants to pass it on to the kernel based on whether the signature is correct. But even if it fails the signature check, the RAM disk is still in memory. So we can use PMD and VMD to construct a RAM disk out of that portion of memory that it temporarily stores our upload in. And then this basically allowed us to boot from an unsigned RAM disk right away and allow us to flash our first bootloaders. So, we learned a lot from this process. We now have adequate control over the iPhone's hardware to even run Linux on it. So that's basically where we are at. And I'll pass it to MuscleNerd to describe the baseband firmware.
Big computer, I can hardly lift it. All right, I'm MuscleNerd. I'm part of the team is sort of divided into baseband guys and S5L guys, although there's a little bit of crossover. I've spent most of the last few months on the baseband side. The goal on the baseband side is to remove the SIM carrier lock. We want it completely gone. For the first-gen iPhone, there was a good reason to do it because there weren't any markets that, other than the US, that you could use the iPhone. So there was a big push to get the first generation unlocked. The next generation, obviously, it's open to a lot more markets out there, but there's still some valid reasons, other than just the challenge of it, to get a software-based or a non-Apple-based unlock into the phone, mostly for travel purposes and just moving between the markets. The baseband in both versions of the phone is run by a system on chip called the S Gold. There's the S Gold, original S Gold and the S Gold 3. It's a full system on chip. It's completely different from the S5L over on the application side. It is connected to the S5L through some limited hardware means, some serial lines, some GPIOs, some I2S, and some DMA, which is used for audio mostly. There's some scouted radio peripherals on that side. There's some unique IDs that are permanently etched into your S Gold and into your NOR that holds your your firmware. They uniquely identify your phone, and they'll come into play a little bit later. The second generation also has GPS. That's sort of a hardware overview. Software overview, it's sort of got the same rhyme as the S5L side. There's a sequence of loaders. Some of them are, that first one, the boot ROM, is based in hardware. We believe it's masked ROM. We hope it's not, because if it's not and we do something stimulating enough to Apple, they may go off and try to reprogram the boot ROMs in the field, and that would be glorious to see, because we could reuse that ourselves. But we believe it's in masked ROM. So the boot ROM loads the bootloader, which loads the firmware, which is that humongous body of code where all of the action takes place, most of the action. So that includes Nucleus, which is a common embedded operating system, the GSM stacks, the SIM support, STK support, and all the things you'd expect from the radio. So there's this sequence, and what I'll do in the next few slides is describe a little bit more detail each of those components. Oh, I forgot these two. There's what they are calling EEPROM and NVRAM, which are really just different parts of the NOR, but they're in parameter blocks, which are smaller, so you can program them faster. These hold things that, two different things that are tied to the baseband and things that are tied to your phone. For example, your Wi-Fi is calibrated at the factory, and there's a unique set of calibration data that was determined at the factory that works with your particular RF chip, and that's specific per phone. So some of it changes depending on the baseband, and some of it never changes unless you have a different phone. Now, the big thing about the baseband, and the most irritating thing, is that there's no DFU recovery mode. And I've always been jealous of PlanetBeing and WizDaz and Pumpkin and all these guys, because they always had a fail-safe to basically give them a free pass to do everything you can think of to the phone. Some of us at several points have completely erased the NOR and completely invalidated the LLB and things like that. And what happens if you have an invalid LLB in there, which is that sort of that second stage, is your phone basically just rapidly flashes white and black with like these horrible looking sear marks going down the screen. And it's very scary to watch, and you think it's completely gone. And we've nicknamed it Christmas tree mode, ZF. But as bad as it looks at the time, as long as you're good with your timing of your fingers, you can always enter DFU mode and recover from that. There is nothing like that in the baseband. There are things you can do on the baseband to the NOR or to the images in the NOR that can permanently brick your phone. And on the first, I mentioned this fake blank thing. Well, I'll get into fake blank later. Okay, so now each of the bootloaders. So the boot ROM just is your basic hardware setup. It maps some of the tightly coupled memory. It maps the external NOR to come into the address space, sets up the serial. Then it goes through a sequence of checks. It goes off and checks to see if the NOR is blank, and it doesn't really check to see that the whole NOR is blank, but it looks for certain key locations to see if they're blank. If it is blank, then it allows, through the serial port, you to upload your next stage loader. If it's not blank, it will, if the bootloader is not blank, it'll go off and load it. In the second generation, but not in the first generation phone, the serial payload that you give to the boot ROM has to be signed with an Apple certificate. That was not true in the first gen phone, and we actually made use of that not being true in the first gen phone quite a lot, because it gives you really low level, very early access to the baseband CPU. Also in the second generation phone, the bootloader itself, which would normally be the next stage of the process, is first signature checked to make sure that it's not been tampered with. And if it does not match the signed hash, then it just won't load it. It will just stay there in the boot ROM and spin. That wasn't true in the first gen phone. The bootloader, which is this next step, is the first few NOR sectors. It has a couple different, sort of orthogonal entry points. Two of the entry points are used for normal versus service mode, but there's also like this completely separate bit, which is normally enabled only by having a certain bit in that chip ID that I mentioned earlier be set. And if that bit is set, then it's considered a trusted or a development device or an engineering device. And it doesn't enforce any of these things I'm about to talk about in the next few slides. The few details, the bootloader in the first gen phone, the NOR sectors are in NOR terminology, they're locked down. So there's actually not only are they not normally erasable, but even if you had the authority to erase them, you'd have to lift a signal on a pin to allow that to go through. It's like an extra lockdown measure. In the first gen phone, the bootloader, and this is important, it's always there in NOR, and it's used, and it's invocable. It's very easy to invoke, actually. And that bootloader itself, and the reason, I don't know if bootloader is an official term or whether it was developed by the community, but it's that bootloader that allows you to go off and program the next stage of the sequence, as long as you pass certain checks. And one of those checks is this next item, the signature check on the firmware. So the bootloader, I don't think 3.9, but 4.6 bootloader in the first gen phone does signature check the firmware. So there is, except for the bootloader itself not being checked, I guess the chain of trust begins at that point. In the second gen phone, unlike the first gen phone, that interactive loader is not there in NOR. It's not permanent. You actually have to upload it. And not only do you have to upload it, it's actually a multi-stage upload. You have to first upload a payload that the boot ROM accepts with one set of keys, and then as long as you've got the authority to upload that image will then go off and load a second bootloader with a separate set of keys. So there's this division of trust in this loader over loader protocol. And it also does this signature check of the next stage. That next stage being the firmware. So the firmware is where, everything except for the booting happens in firmware. So this is where your radio hardware gets set up, and the stacks get set up, and the SIM starts, and the STK starts, and everything starts. This is where all the action is. Once the firmware is up and running, which is done with the Nucleus OS, which I mentioned earlier, it's basically, it's the whole program on the phone. The only thing that would bring it out of that operation mode would be a crash or power off or something like that. The firmware can be updated, obviously, and this is the next few slides are a brief description of that update. You basically reboot the baseband with the control signal, which is easy to do. You ping it, you get it to enter the service mode that I talked about. In the second gen phone, this is where you do that multi-stage loading of the loader itself. So there's the security loader and this RAM loader. But in the first gen phone, it's a lot easier. You just reset it and you just ask it, please go into service mode. At that point, all right, so that's where they differ. At that point, they sort of join up again, and what they do, you basically give these loaders what's called a sec pack that describes, it's a file that's signed by Apple. It's verifiably signed by the bootloader, and it defines what NOR addresses you're allowed to touch, what the signature of the firmware you're about to load is, and so it's a signed package describing what's about to happen. If any of those fields are mutated in any way, the signature fails, and whoops, what did I do? Help! Anybody good with OS 10?
Damn you, Google. Google updater for the win.
Why is your Wi-Fi?
Serious.
That's right.
Let's turn the Wi-Fi off.
Yes, that's right. Yes. Okay, if all those things pass, then you send it the firmware, and the bootloader takes care of updating the upper part of the NOR. So here's the chain of trust. I'm going to do it sort of in reverse order. The SIM carrier lock, which if you recall is our ultimate goal, is enforced by the firmware. Definitely do not want to go into the detail here because there's a lot of detail here. But there are basically tables in there that describe to the phone whether the lock even exists, it's tied to those two IDs I mentioned earlier, the chip ID of the S Gold and the NOR itself. There's T encryption, there's RSA encryption, there's all the stuff that goes on in the what's called the SEC zone. And so the only difference between a locked and unlocked phone in the official sense is the tables that are encrypted in the SEC zone. The firmware itself is identical, the baseband is identical, the boot ROM is identical, everything is identical. It's just the SEC zone which is uniquely tied to a given phone's chip ID and NOR ID. That's why you can't just take an officially unlocked phone, somehow copy the firmware over to an unlocked phone, a locked phone, and somehow make it unlocked, because that SEC zone would not verify the bootloader and the firmware itself would try to decrypt it using that phone's chip ID and NOR ID, and it just would be bogus. It wouldn't recognize it. All right, so continuing with the chain of trust. So the SIM carrier, I'm going back and forth. SIM lock is enforced by the firmware. The firmware is integrity checked by the bootloader. There is a signature there. It's verified by the bootloader. And if that check passes, the bootloader just stops. It doesn't go any, you can't, it's basically non-functional. All right, so, I'm sorry, I should not keep going back and forth. So, this is the check for the existing firmware. The existing firmware will not be run if the integrity check fails, which means that somebody has come in after the fact and changed the NOR on you. There's also the update process, right? So new firmware is verified by the service mode loader, and it's signed with all the usual checks. And then this loader overloader stuff. And here's sort of a similar thing on the S5L side. On the first gen phone, the bootloader, which is that first thing in NOR, it's the first programmable thing that you can actually touch. The bootloader is not integrity checked by the boot ROM, which is that thing that exists in hardware. So there's no integrity check done there. So if you have the means to change the bytes in that NOR for the bootloader, you can basically take control of the baseband. There's only a few checks to see whether or not, maybe there's garbage in the NOR, so there's a few magic value checks, but it's not an integrity check. As opposed to the second gen phone where the boot ROM does a full integrity check of the bootloader. Oh, and this last point is important. Am I running out of time? This last point is important. The boot ROM, after it hands control to the bootloader, almost the first thing the bootloader does, like not even 20 instructions into the sequence, is it maps out the boot ROM, and it maps it out in a way that you can never bring it back without doing a full reset again. And we see to me, what looks like port knocking, which is used to basically tell the boot ROM to never come back. And that's a limitation, and hopefully we'll have time to get into that at the end. Okay, so now onto the exploits. In the first gen phone, there were 2 bootloaders that were published. There were more that were actually existed on that first package that was put out by Apple. But the only 2 that were really in play were this 3.9 and the 4.6. Without boring you, the bugs in 3.9 basically allowed a few things. It allowed you to bypass the SecPack restrictions simply by doing some address manipulation. In other words, the SecPack said you cannot program at this address for this many bytes, but it didn't say that you couldn't start a little bit earlier and then progress right through that previously protected section. So all you had to do was back up where you wanted to write from, write garbage if you wanted to, and then write what you really want to write. So it was just an address bug, basically. There's also this Blankenbacher attack, which is different from this SecPack restriction hack. What it does is that check that's done by the bootloader as to whether the firmware is okay, uses RSA, uses an exponent 3 version of RSA, which is subject to this Blankenbacher attack, which is basically a way to, what? I'm sorry? which is basically a way to forge the RSA in a way that it looks like it passes to a poor implementation of RSA. And it's interesting because, yay, because this Blankenbacher attack actually comes into play in a few places. Not only does it allow you to forge the firmware, it actually is used in the sec zone. And this iPhone SIM-free solution, which was the first software solution out there for the first-gen phones, actually used this Blankenbacher attack on the sec zone to mutate the tokens in a way that they weren't really valid tokens. If you actually use the chip ID and the NOR ID of the phone itself to try to verify these tokens, it would fail. But if you just blindly used RSA on them, it would look like it passed. The end result would look like an unlocked token. Those were the two primary bugs on the 3.9. 4.6 had some different bugs. Allowed you to bypass SecPack restrictions again. The SecPack is a constant nuisance, and anything you can do to get rid of its restrictions is good. There was basically a different version of the -400. Well, I shouldn't say it. There was basically another way to trick the address verification of the SecPack. And the second point is technical. I won't go into it. On the first-gen phone, again, the boot ROM doesn't check the bootloader's integrity. Fake blank, I'll briefly mention this. There was this application we put out called boot neuter. It allowed you not only to program 3.9 or 4.6 into your phone, it allowed you to neuter it or to fake blank it. Neutering was a way to basically permanently remove all the SecPack checks on that phone. So it was basically a patch in the bootloader that would forge that bit that I talked about earlier that made it look like a development phone. And we called it neutering, and it would basically take the SecPack completely out of the picture. Fake blank was just a way to have your cake and eat it too. It was a way to allow the phone to normally boot, but if you really wanted to get in there at the low level and give a serial payload before the bootloader has a chance to run, you could actually do both. Normally you wouldn't be able to. The very last sort of exploit that was out there on the first-gen phone was JerrySim. It was basically a SIM card-based hack which allowed code execution, unsigned code execution on the baseband due to a buffer overflow. JerrySim was leaked, and we presumed it to be burned. We presumed it to be lost forever because at the time it was leaked, it was around the time the 3G started to be developed, and there were no further updates to the first-gen firmware. But they had all this time to see what we were exploiting in JerrySim. Am I running out of time? All right, I'm going to speed it up. All right, well, this is the core of what I'm talking about. There are exploits for the second-gen phone. Chain of trust is tough to beat. It's not impossible to beat. It would be possibly easier to beat if we had an image of the boot ROM, but we don't. So for now, we're just going to avoid breaking the chain of trust. We're just going to try to patch the firmware once it's running out of RAM. In a way, it's safer than reflashing NOR. Reflashing NOR has a bunch of risks that are usually user-related. If the user does something at the wrong time, they can put the phone into this permanent brick mode that I talked about. This doesn't have that risk. There are two parts to it. There are two parts to the soft unlock. There's the unlocking code itself, which is your payload. It's your ultimate payload. It's what you want to get into the running firmware and allow it to coexist with the running firmware. And basically what you do is you reprogram the firmware. While it's in RAM, you basically change the decision tree that would normally take place about whether a SIM that's just been inserted should be allowed to operate. The actual, sort of the development of the unlocking code takes a little bit more initial investment because you have to sort of understand more about what Apple has intended in the firmware. That's the downside, but once you've got that work out of the way, the unlock code itself, the principle that the unlock uses, is reusable over and over again as the firmware changes. I definitely do not have time to go into the into the first demo that we did of code injection, but that's on our blog. All right, so that first part is the unlock code. It's the body of code that you want to run on the baseband. The second part is important. You need to get that code into the firmware, into the running firmware. You need to inject the exploit. You need to do it in a way that does not crash the firmware, because once the firmware crashes, that whole boot sequence takes over, chain of trust is reinforced, RAM is wiped out, anything that you may have patched in RAM is gone, and you're at square one again. What's interesting, the reason I mentioned JerrySim earlier is JerrySim was actually still present in the first release of the iPhone 3G. The hole was still there. They didn't actually fix it. Unfortunately, they did fix it soon after. They fixed it during the beta cycle before 2.0.1. This injection only works if you're jailbroken. The jailbreak is very important to the iPhone 3G soft unlock. You can only do this if you're running software that Apple does not want you to be running. The second bullet here, it's kind of in the wrong place, but Apple is definitely going to be closing any of these injection exploits as they're used, in a way that's similar to the jailbreak for the first-gen phone. Every time we did the jailbreak for the first-gen phone, they patched the hole that was used. Similarly, with the soft unlock, anytime they see how we're injecting this unlock code itself, they are going to fix it, and it's going to go away real fast. So injection holes are easy for Apple to identify because we basically use them. But the important, in my mind, what's important is that, fine, there'll be this cat and mouse game, as Steve Jobs mentioned over and over again, between us and Apple, between the community and Apple. But we really believe, or I really believe, that the unlock code that's injected, even though the injection may change, the code that's injected is not fixable. And hopefully I'll explain it in a second. There was a live demo of the unlock a couple days ago. I don't think we have time for that. Okay. This is on the blog, but this is, whoa. How do I do that from in preview mode? I can't do it. That's not playing. Like, I thought I could just click on it to. Anyone use Keynote? It's on the blog. No. Okay. Anyway, the demo's on the code on the blog. What helped with the development of the soft unlock was IDA. It was not just the second-gen phone, but the first-gen phone. Again, we had the unencrypted flash files of the baseband firmware, so we were able to reverse engineer without even needing to have it on the phone. We were able to statically reverse engineer different stages, or the different stages involved in the baseband boot. JerrySim itself was very important, it turned out. During that long gap I mentioned, where Apple wasn't really doing any updates to the firmware, we were actively using JerrySim to really, we had an early release of the 1.45 firmware, and we had a lot of time to sort of peek and poke at that firmware using JerrySim. So even though JerrySim wasn't really used in the field, it was used internally a lot. What also helps is we have team members that have these different hardware rigs for probing for these injection exploits, basically. So this is from W, or W underscore, I think. This is a rig that he has to basically, without going into the details, it's basically a MUX there that muxes between the real SIM card and a PIC controller. And he's allowed to, it allows him to quickly sort of fuzz the baseband for holes in the SDK and for other parts of the SIM. Obviously, the internet is a big help because there's a lot of, the S Gold and the S Gold 3 is not unique to Apple. Other phones use it. There are other groups doing similar things for other phones. There are address maps. There's all sorts of low-level hardware things that are identified just because there were simultaneous parallel efforts for other devices. There's nothing left to be done for the first-gen phone. The application side is completely pwnable. There's no way they can fix it. We have complete control over the baseband for the first-gen phone. Second-gen phone, for now, soft unlock is great. It's a great first step. It'd be nice to have a permanent unlock similar to the first-gen phone. The problem with the soft unlock is every new baseband version, people will update to it blindly. They'll lose the soft unlock, and they'll have to wait for a new injection exploit to be found to inject the unlocking code. But the unlocking code itself, again, won't need to be changed. It may need to be relocated because the firmware changes location. But the code itself, it's not taking advantage of a bug that Apple does in the firmware. It's basically just reprogramming the firmware. And there's very little that Apple can do to change that. We're basically just changing their decision dynamically in RAM. This is the last slide. These are the two remaining things. We really need to find the boot ROM because we really would like to have a more permanent unlock, assuming there is an exploit that can be found and used to break the chain of trust. And there's this other side project. There's a lot of utility in dumping GSM packets and logging them, and there are a few devices that cost very little that allow you to do that. And the technique used in the soft unlock, because it's running along with the existing firmware, interactively, cooperatively, it's running there, it can sort of deal with the same packets that are being processed, allows basically you to dump and log. And that's the last slide. Oh, man. So, we have how many minutes? We have 3 minutes, I guess, for questions.
Any questions?
Good questions. Come on.
For any of this, for anyone, including our Phantom Dev members down there.
English, Russian, whatever, you know.
If you have a question, yell it.
Are there any questions at all? Do you want to come up to a mic?
Somebody over there. Yes.
Hello. I've heard Apple is now trying to attack you on OS X directly. Is there any truth about them trying to block you running your Pwnage tool on OS X? Or
that was actually a bug. We believe it was a bug, not a specific.
Wishing actually had a chance to look into that.
Yeah, it looks like it's actually a bug, and in fact, iTunes itself breaks also with the same bug, so it looks like it's not specific to Pwnage tool.
So it's not a malicious attack by Apple, it's simply a bug.
We think it'll go away real soon on its own. But there's also a fix for it, and it's on hackintosh.org.
Is it possible to dump the ROM of second generation devices by just unsoldering the chip, the ROM chip, and then soldering it to a test board and dumping it from the hardware perspective?
Not the boot ROM, no.
Where is it stored? Is it inside the chip or?
I didn't understand that full question.
Can you desolder the chip and dump the
yeah.
boot ROM?
Yeah, you sure? Well, all right. So there's two answers to that, depending on the phone. The first-gen phone, you could definitely unsolder the NOR chip. You could reprogram the bootloader, and with the reprogrammed bootloader, you could have whatever firmware you wanted in there. Because again, the boot ROM did not check the bootloader. On the second-gen phone, you cannot do that because of that check that's done by the boot ROM. If you try to muck up that bootloader in any way, it just won't boot.
Yes, but I mean, if you open a phone and just take the ROM chip and dump it with a hardware dumper.
So when we're talking about a ROM chip, we're talking about something, it's not actually an external chip.
Oh, right,
it's buried inside the processor.
Oh, yeah, okay.
Yeah, remember that SoC block diagram I showed with that 100 rectangles? The boot ROM is one of those 100 rectangles.
Any more questions?
There's some guy there.
Yeah,
Good night.
Somebody there in a fetching yellow T-shirt. He's.
In the lecture before this, downstairs in S2, there was a guy who was shaving the tops of the chips off and then sticking pins in to read the data inside the chips.
Yeah, we'd love to talk to that guy.
So I was just thinking, yeah, that would be a way to dump the memory out of the chip.
Absolutely, definitely.
I'm wondering if you get hands on an Italy iPhone, if you cannot just dump the bootloader from this one and reprogram.
Sorry, could you speak up? We can't hear you.
I said, I'm just wondering if you get your hands on an Italy iPhone, if you just can dump the information from this one and load it in your own bootloader. The Italy iPhone is a free one, as you well know. So I wonder if you can just dump the information out of it
Are you mixing the phone generations, or are you saying with the second gen?
The second generation iPhone, what you buy in the land called Italy, is free. So there you can put in any SIM card you wish. I bought one and I have an O2 card in it, and I activated with the O2 card and I said no problem. So I was wondering if you just can dump the bootloader by itself and find out the information, why they can have it for free and other one are locked.
Now, I tried to address that earlier. The code base itself is identical. There's nothing different between the code in a locked and an unlocked phone. The only difference is in the sec zone. And the sec zone has the advantage, or the whole purpose behind the sec zone is it's unique to your phone. It cannot, the information in that sec zone cannot be copied. If you take, by way of example, if you take an unlocked phone, officially unlocked phone, and copy that sec zone into another unlocked phone, you'll break that second phone. It won't even function anymore. You just cannot copy that sec zone.
About 5 minutes left. Any more questions at all?
5 minutes. Oh my god. Wow.
Don't be shy. Come on.
All right. Well, shall we just wrap it up then?
Any more questions finally? No?
Is there any motivation left for you?
So the question at the front is, have we had any communication with Apple? And from the beginning of the project in 2007, we've not had one single communication from them whatsoever. And,
I talked to Wozniak, and there's a picture of him holding up the phone on our blog.
So Woz is a fan, and I've sent him some email and stuff, but no, they haven't contacted us formally with any cease and desists or anything like this. We're very careful about what we ship. There's no copyrighted code in there, and that's the reason we think we're not hassled by them. But they're pretty nice to us. So
they do fix the bugs, though.
Yeah, they fix the bugs. So
Sorry? Is there any motivation left?
Sorry?
Do you have enough motivation for the next iPhone generation?
Oh yeah, of course.
Motivation.
It's fun, isn't it?
Okay, one last question.
I got an iPhone in Netherlands, and
Speak up, please.
I got an iPhone in Netherlands, and they give you SIM unlock. And once you connect the iPhone to iTunes, they somehow unlock it. So what would they...
Could you speak up, please? We can't hear you.
I got an iPhone in Netherlands from T-Mobile.
Yes.
And once you pay some extra money, they will unlock it for you.
Yeah. So I think it's the same question again. No.
Right.
No. Okay, well, thanks very much, ladies and gentlemen, and we'll see you later. Thanks.